Hey everyone, and welcome. Today, we're diving into the fusion of two of technology's most powerful and, let's be honest, mind-bending fields, quantum computing and artificial intelligence. This isn't just a small step forward. We're talking about a whole new reality for what's possible.
But that brings up a huge question, one that really gets to the heart of this whole revolution. How do you actually teach a machine to think quantumly? I mean, how do you even begin to build an AI that plays by the wonderfully strange rules of quantum physics? Well, that's the puzzle we're going to start piecing together today.
And that's where something called quantum machine learning, or QML, comes in. The promise here is, well, it's enormous. We're talking about having the ability to solve problems that are literally impossible for even the biggest supercomputers we have right now. It's incredibly exciting stuff for sure. But, before we can jump in and start building these game-changing models, we have to understand the blueprint. We've got to get a handle on the foundation that this entire field is built on. So how do we crack the code of this new reality? The best way to think about it is like you're learning an entirely new language, a language that describes how the universe works at its most fundamental, most granular level. And if you're thinking, oh, he means a programming language like Python or C++, you're on the right track, but not quite there. The real key to unlocking this world isn't just some new code. It's the language, the one that underpins everything else, the one that actually describes the quantum world itself. And that language is mathematics. It is the universal tongue of quantum computing. Without it, things like quantum states, algorithms, and AI models are basically impossible to wrap your head around. It's the master key that unlocks this entire field. Okay, so if math is the language, what's lesson one? Well, the whole thing is built on three essential pillars. You can think of them as the grammar, the system for understanding outcomes, and, well, the absolute rules of the game. Let's break them down. So here they are, the big three. Linear algebra, that's our grammar. Then there's probability theory, which helps us make sense of the outcomes. And finally, quantum mechanics, which gives us the unbreakable rules. These three work together to form the complete foundation for quantum machine learning. First up, linear algebra. This is the absolute core grammar. It gives us our nouns and our verbs. In this language, the fundamental units of information, what we call quantum states, are basically just vectors. And the things we do to them, the operations, are matrices. Next, we need a way to understand what we're looking at. See, quantum systems are, at their heart, all about probabilities. When you measure a qubit, you don't get one single definite answer every time. You get a range of possibilities, each with a certain chance of happening. Probability theory is the tool that lets us calculate and actually understand those chances. And finally, quantum mechanics. This is the official rulebook for reality itself. It gives us the physical laws. You've probably heard of things like superposition, where a qubit is in multiple states at once, and entanglement, where qubits are mysteriously linked. These rules are what make quantum computing so incredibly powerful. Okay, I know, 3 pillars might sound like a lot to take in at once. So let's zoom in. Let's boil it all down to the single most important concept that ties everything together. This is the very first word you need to learn in this new language, the vector. And here is the truly amazing part. If you've ever touched classical machine learning, you already think in vectors. You just might not realize it. This whole quantum world, it isn't nearly as alien as it might seem. The big aha moment is right here. Just look at this. On the left, in classical ML, we might represent a person with a simple vector, right? Height and weight. On the right, in quantum computing, we represent a qubit state with a vector. I mean, look at them. Structurally, they're the same thing. They are both just a list of numbers. So what do these quantum numbers 0.6 and 0.8 actually mean? Well, these are called amplitudes, and they are the secret sauce. To figure out the actual probability of measuring the qubit in a specific state, you just square its amplitude. It's that simple. So, the chance of measuring state 0? It's 0.6 squared, which is 0.36, or a 36% chance. For state 1, it's 0.8 squared, giving us a 64% chance. And check this out. This is where one of those fundamental rules kicks in. What happens when you add those probabilities together? 36% plus 64% equals 100%. It equals 1 every single time. The total probability must always add up to 1. That's a core principle, and it's what makes sure all this math actually lines up with reality. So there you have it. You've officially taken your first step. You've learned the most fundamental word in the entire language of quantum AI, the vector. So now we can start thinking about what's next. How do we go from speaking just one word to writing a full sentence?
Let's do a super quick recap. QML is where quantum computing and AI crash into each other. The language it speaks is math, built on 3 pillars: linear algebra, probability, and quantum mechanics. The most fundamental concept connecting them all is the vector, and a quantum state is really just a special kind of vector that's all about probabilities. You've just successfully decoded the most basic unit of all quantum information. You've learned the very first word in an incredibly powerful new language. So the only question left is, are you ready to write a sentence? Thanks for joining us.